This model shows an ideal FHP bearing design optimized for maximum service life and low cost, using the Permawick lubrication system in horizontal shaft orientations. The stamped end shield forms a nest for the self-aligning bearing. Note the turned-in lip at the bottom of the bearing nest. This feature allows an area for oil to puddle and later to be reabsorbed by the bearing. This area can also support the addition of an O-ring, which reduces oil loss on the external side. This end shield design includes integral tab downs to secure the internal cover instead of rivets. Note that no gaskets or sealers are required. Proper Permawick placement eliminates leaks, simplifying the design and maximizing reservoir capacity. The sintered metal bearing, impregnated with Permawick oil that matches the Permawick in the reservoir, is placed in the nest of the end shield. The bearing is spherical to provide self-alignment. Note the chamfer on the ID of both ends of the bearing, which guides the shaft into the journal without damage and allows oil to move outward onto the face, lubricating axial loads. The internal oil cover is designed to hold the maximum amount of Permawick material. Note the burr or turn-down lip at the top of the cover. This lip is useful for holding the Permawick material in place inside the cover and eliminating potential leaks. The ID of the cover should be at least 1/4 inch larger than the OD of the bearing to allow for easy injection of the Permawick. This design floats the retaining spring. The spring is not trapped between the cover and the end shield. Floating the spring reduces the risk of sideloading of the bearing. The spring retainer should have an odd number of fingers with a minimum opening of 50% of the surface area. An odd number of fingers ensures that at least one inject hole will clear the metal. The Permawick injection nozzle comes down and locks the 4 tabs down over the internal cover while it injects the Permawick material. Once the operation is complete, the motor is permanently lubricated. Permawick fills all of the nooks and crannies of the assembly, maximizing oil storage without the need for seals or gaskets. The Permawick is injected to maximize contact with the OD of the bearing to ensure positive oil transfer. Permawick is available in mineral and synthetic blends for all motor applications. Bearing service life can be greatly increased by holding 2 key specs on the shaft: finish and hardness. Shaft finish should be approximately 12 to 15 RMS. Shaft hardness should be a minimum of 95 Rockwell B. A combination of hardened shafts and synthetic oil adds only pennies to the cost of the assembly, but can double bearing service life, reaching 40,000 hours for a fraction of the cost of ball bearings. This is a huge competitive advantage for motor makers. The addition of a slinger washer will greatly increase motor life. The slinger washer should be tight and rotate with the shaft. For light loads, a nylotron slinger can rub against the bearing. If higher thrust loads are anticipated, a hard steel washer should be added between the slinger and the bearing. As the shaft rotates, the journal's oil film flows horizontally where it meets the slinger washers, the larger outside diameters of which sling by centrifugal force the oil to the respected oil catchers containing Permawick material. The Permawick material supplies oil to the bearings on a continuous basis so the bearings remain 100% impregnated with oil at all times. Permawick's ability to inject, combined with its controlled release rate and greater storage capacity of oil, make it the best choice for FHP motor lubrication.